Hey everyone, looks like you're getting ready for that ultrasound physics exam. So we're diving into sound waves and transducers and all that fun stuff to help you totally ace it. We've got your practice questions right here, and we're going to break it all down, make it clear and simple, maybe even have a little fun along the way.
It's pretty amazing how ultrasound uses basic physics to show us what's happening inside the body. Once you get those principles, those images really start to make sense.
Okay, so let's start with something basic. One of the first practice questions is all about sound waves. It asks about those regions, where the particles are less concentrated. What are those called again?
Those are called rarefactions. So sound waves are basically variations in pressure that are moving, right? Imagine a slinky and you're pushing and pulling it. You get those areas where the coils are all bunched up and then areas where they spread out. Those spread out parts, those are the rarefactions. Ultrasound uses those, the compressions and rarefactions. It sends out these pulses of sound waves and then it listens for the echoes that come back. Kind of like how bats use echolocation.
So it's like a super fast game of acoustic ping pong using those compressions and rarefactions to make pictures, right? This next question is about how those sound waves actually travel. They mentioned this thing called propagation speed. What is that all about?
Oh, propagation speed is just the speed at which sound travels through whatever material it's in, the medium. Think about how sound is different in air versus water. That's because the speed changes based on stuff like the density or the temperature. Those are called acoustic variables.
Okay, that makes sense. So the denser something is, the faster sound goes through it. So how does all this relate to the actual ultrasound machine? The next part in the practice materials is all about transducers. I see phased arrays, annular arrays. To be honest, it's a little overwhelming.
Think of transducers as the heart of the whole system, right? They're what send out and then pick up those sound waves we were talking about. They change electrical energy into sound and then back again. It's like they're both the microphone and the speaker. There are different types of transducers, each with its own pros and cons, but the ones to really know for your exam are phased array transducers. These are really cool because they do something called electronic steering, so no moving parts. Imagine a bunch of tiny little speakers, and they're all firing sound waves, but with slightly different timing. That lets them sweep the sound beam across the body, which is how we get those real-time images on the screen.
Wow, that's like a choreographed dance of sound waves. But there's a note here about grating lobes. What are those, and why are they important to know about?
Grating lobes are kind of like a side effect you can get with phased array transducers. Basically, there are these extra beams, sort of unwanted, that can pop up off to the sides of the main beam. Imagine shining a flashlight, and instead of one beam, you get these little stray beams coming out at weird angles. Those are like grating lobes. And the problem is they can sometimes mess with the image, make things look blurry or distorted.
So those grating lobes can create these little ultrasound illusions, right? That's a good way to think about it. But how do we make sense of those echoes that come back? This question mentions demodulation. Is that part of how the image gets created?
Demodulation is super important. It's how we turn those echoes into something we can actually see. Basically, we take those complex sound waves and pull out the important information from them, like how strong they are, how fast they're vibrating, that kind of thing. Then that information gets used to figure out how bright and where each pixel should be on the ultrasound image.
So it's like translating the sound waves language into a picture we can see. All right, let's talk about resolution. I see a lot about axial and lateral resolution in your prep materials. Can you break down what those mean and why they matter?
Resolution is all about how much detail you can see in the image. Think of it like looking at a photo. A high-res photo is super crisp and clear. Low-res looks blurry, right? In ultrasound, we have two main types of resolution to think about: axial and lateral.
Okay, so what's the difference? I always mix them up.
Axial resolution is about, can you tell apart two objects that are close together but along the direction of the ultrasound beam? So can you tell apart two dots when they're stacked on top of each other? Lateral resolution is about telling apart objects that are side by side. Can you tell apart two dots when they're next to each other?
So axial's about depth and lateral's about side to side detail.
Exactly. And here's a key thing for you since you're prepping for this exam. Axial resolution is usually better in ultrasound than lateral resolution. That's because actual resolution comes from the length of the sound pulse, and those pulses are super short. Lateral resolution, though, comes from the width of the ultrasound beam, and that's usually wider than the pulse length. Think about it like a flashlight. A narrow beam of light gives you a nice, sharp spot.
So understanding that difference helps me choose the right transducer and settings to actually see those tiny details I need to find, right? Speaking of seeing things clearly, let's talk about those pesky artifacts that can, like, trick you in ultrasound images. These practice questions mention something called parallel line artifacts. What's the deal with those phantom lines?
Artifacts. They can be tricky. Parallel line artifacts, they're also called reverberations. They happen when the sound beam gets trapped between two really strong reflectors, like the walls of a cyst or a blood vessel. Imagine the sound wave bouncing back and forth between them, creating all these extra echoes. And those echoes show up as equally spaced lines on the image.
So it's like the sound waves are stuck in an echo chamber. Are there other types of artifacts I should be on the lookout for?
Oh yeah, absolutely. There's shadowing, which happens when something really dense, like a bone, blocks the beam. It's like a shadow from a flashlight. And then you've got edge artifacts. These pop up when sound waves bend around curved structures, so you get these bright or dark lines at the edges. It's a bit like how a straw looks bent in a glass of water. The key is being able to spot these artifacts so you don't mistake them for something real.
Wow, so ultrasound can be pretty deceptive sometimes. Okay, let's shift gears and talk about Doppler. I've got a bunch of questions about Doppler shift, how it's used to measure blood flow. Can you explain that in a way that, makes sense?
Doppler is all about detecting changes in frequency that happen because things are moving. Think about the sound of a car horn as it passes you. The pitch changes, right? That's the Doppler effect. In ultrasound, we use this to figure out how fast blood is flowing. Basically, the faster those blood cells are moving, the bigger the frequency change we pick up.
So that Doppler equation, it pops up in a lot of the practice questions. That's basically how we go from that frequency shift to actually measuring speed. It seems pretty complex.
The Doppler equation definitely looks intimidating, but all it's really doing is taking into account a bunch of factors, like the frequency of the ultrasound wave the machine sends out, the frequency shift caused by the moving blood cells, how fast sound travels in tissue, and the angle between the ultrasound beam and the blood flow. Plug all those into the equation, and boom, you get the velocity of the blood.
Wow, that's a lot to keep track of. Can you give me an example of how those things would actually affect, like, a velocity calculation in a real situation?
Sure, imagine you're using Doppler to measure blood flow in an artery. Now, if the angle between your ultrasound beam and the direction the blood's flowing is too steep, the velocity you calculate is going to be lower than the real velocity. That's because the cosine of that angle gets smaller, which makes the whole equation's result smaller. So you want to get that angle as close to 0 degrees as you can for the most accurate reading.
That makes a lot of sense. Speaking of things that can be confusing, I see a lot about the colors used in color Doppler. I know blue usually means flow away from the transducer, but does that always mean it's venous flow? I feel like there's a trick here.
Yeah, that's a really common misunderstanding. Blue in color Doppler doesn't automatically equal venous flow. It just means the blood is moving in the opposite direction of whatever color they're using for flow towards the transducer, which is usually red.
Wait, so blue doesn't always mean venous flow. So how do I know what I'm looking at?
It depends on how the transducer is positioned and how the blood flow is going compared to the beam. The key is to check that color bar on the screen. It tells you which color is which. You also got to think about the anatomy. Are you looking at an artery or a vein?
So color Doppler is showing relative direction more than, like, specific types of blood vessels. That's really important to remember. This is all starting to make more sense now. So how does all this physics knowledge actually translate to, like, picking the right settings on the machine?
That's where things get really interesting. Understanding the physics, letting them make good choices about stuff like the transducer frequency, how much power to use, the gain, the focus, all that. For example, if you're trying to see something deep, you'll want to use a lower frequency transducer because higher frequencies get absorbed more by the tissues.
So it's like picking the right tool for the job based on what you're trying to see and how deep you need to go.
Exactly. And by knowing how resolution works and artifacts and Doppler, you can tweak your settings to get the clearest, most accurate images possible.
This is all incredibly fascinating. I'm going to really get a handle on, like, the basics of ultrasound physics. But before we go any further, I want to make sure we hit one more thing that comes up a lot in your practice questions. Attenuation. What is attenuation and why should I care about it?
Attenuation is just the fancy word for how the ultrasound beam gets weaker as it travels through tissue. Imagine shining a flashlight through fog. The further the light goes, the dimmer it gets, right? Attenuation is like that, and it's caused by things like absorption, scattering, and reflection of the sound waves.
So the deeper that ultrasound beam goes, the weaker it gets. Why does that matter?
Well, attenuation has a big impact on image quality. As the beam weakens, the echoes that come back get fainter, which can make it harder to see those deep structures. That's why we need to adjust the gain or power settings on the machine to compensate for it, especially when we're imaging deeper.
So understanding attenuation helps me adjust those settings to get the best possible images, right?
Yep, exactly. It also helps you understand why some structures might look brighter or darker depending on how deep they are and what kind of tissue is around them.
This is all starting to click. I feel like I have a much better grasp on how ultrasound works and how those physics principles actually apply when you're scanning. But there's so much more to explore. We're going to take a quick break, and then we'll dive back into those practice questions to solidify our knowledge.
Sounds good. Ready for more practice questions?
Absolutely. I'm feeling much more confident now that we've got those basics down. Okay, this one asks about something called the intensity reflection coefficient. It sounds intense. Could you break that down for me?
It's basically a way to measure how much of the ultrasound beam bounces back or reflects when it hits a boundary between two different types of tissue. It's a percentage, so a higher percentage means more reflection. Think of shining a light on a mirror. Almost all of it bounces back, right? That's a high reflection coefficient. Now imagine that same light on a black cloth. Most of that light gets absorbed, so the reflection coefficient will be low.
So it's like a measure of how bouncy that boundary is for sound waves. But what determines how much of that ultrasound wave actually gets reflected?
That all comes down to a property called acoustic impedance. It's a measure of how much resistance a material puts up to sound waves trying to pass through it. The bigger the difference in acoustic impedance between the two tissues, the more reflection you'll get at that boundary. It's like trying to roll a ball from a smooth surface onto a rough one. There's going to be more bounce back where they meet.
Okay, I'm starting to see the connection. So knowing about acoustic impedance helps us predict how much of the beam is going to be reflected at those different tissue boundaries. That's pretty cool. This next one asks about frame rate and why it's important in ultrasound. What exactly is frame rate? And what makes it so special?
Frame rate is just how many images or frames are displayed every second. Think of it like watching a movie. A higher frame rate means the motion looks smoother and more fluid, right? In ultrasound, a higher frame rate lets us see those real-time movements inside the body more clearly, like a beating heart or blood flowing through vessels.
So a higher frame rate means like a smoother, more realistic image. But wait, wouldn't a higher frame rate always be better? What are the downsides?
That's a good point. While a higher frame rate is usually what you want, there can be trade-offs. Like sometimes increasing the frame rate can actually reduce the image resolution or how deep you can see. That's because the system has less time to gather information for each frame if it's trying to display them more quickly. It's all about finding that balance depending on what you need to see.
So it's like choosing between a fast-paced action movie with a little less detail or a slow drama with those really intricate visuals. I'm starting to see how all these factors are like intertwined. Okay, this next one brings up a term I've heard but never really understood. Absorption. What exactly is absorption when we're talking about ultrasound?
Absorption is basically when sound energy gets turned into heat as it travels through tissue. It's one of the main reasons why those ultrasound waves get weaker or attenuate as they go deeper into the body. Imagine sunlight hitting a dark surface. The surface absorbs that light energy and turns it into heat.
So it's like the tissues are soaking up the sound energy and turning it into a tiny bit of warmth. But is absorption the same for all ultrasound frequencies?
That's a key point. Absorption is actually directly proportional to the frequency. That means higher frequency sound waves get absorbed more easily than lower frequency waves.
Oh, so that's why you might choose a lower frequency transducer to image those deeper structures, right? To minimize that absorption. This one mentions the Q value of a transducer. I've heard that term thrown around, but I'm not really sure what it means. Can you shed some light on that one for me?
The Q value, or quality factor, is a measure of the transducer's bandwidth. Simply put, bandwidth is the range of frequencies that a transducer can send and receive effectively. A lower Q value means a wider bandwidth and vice versa.
So a lower Q value transducer would be more versatile, like it can handle a wider range of frequencies. But why is bandwidth important in ultrasound?
Bandwidth is key for some of the more advanced imaging techniques. Like harmonic imaging, it relies on the transducer being able to receive echoes at twice the frequency it was transmitted at. So a wider bandwidth helps the transducer handle those higher frequencies better, which gives you a better quality image.
Okay, that makes sense. Now this one brings us back to artifacts. It mentions edge artifacts that can appear when those ultrasound waves hit a curved surface. What are those, and how do they happen?
Edge artifacts are those bright or dark lines you might see at the edges of curved structures in the image. They happen because of how sound waves bend or refract as they pass through tissues that have different acoustic properties.
So it's like the sound waves are getting distorted as they try to navigate those curves.
Exactly, and how much they bend depends on the angle they hit that curved surface at and the difference in the speed of sound between the two tissues.
I'm realizing that ultrasound is all about understanding how those sound waves interact with all these different materials. This next one seems a bit tricky. It says that the acoustic impedance of the backing material in a transducer has nothing to do with the transmission fluid used for coupling. I thought both of those things were important for getting those sound waves to transmit.
That's a good catch. It really highlights the different roles that backing material and transmission fluid play. The backing material is actually inside the transducer, and its job is to absorb any ultrasound energy that's going backwards. That keeps those waves from bouncing around inside the transducer and making extra echoes. It also helps dampen the vibrations of the piezoelectric element, so you get those short pulses we need for good axial resolution. Now, the transmission fluid, that's what you put on the skin. It's like a bridge between the transducer and the body. It gets rid of air pockets that would otherwise reflect a lot of the sound waves, so the ultrasound energy can get into the body efficiently.
Ah, so they have separate but equally important jobs. That clears up a lot of confusion. This one asks about operator controls. It wants to know which control adjusts the transmitted intensity of the ultrasound beam. Is that the same as gain?
That's an important distinction. The control that adjusts the intensity of the beam you're sending out is usually called power output or output power. It's basically like the volume knob on a speaker. Higher power means louder sound waves. Gain is different. Gain amplifies the echoes that come back, making the whole image brighter or darker. It's more like adjusting the brightness setting on your computer screen.
So power is like the volume control for the outgoing sound, and gain is like the volume for the returning echoes. That's perfect. Okay, let's revisit those acoustic variables. We talked about them before, but this question wants a bit more detail. What are they, and why are they so important in ultrasound?
Acoustic variables are basically just characteristics of a material that can affect how fast sound travels through it and how the sound waves behave. The main ones are temperature, distance, pressure, and density.
So if any of those variables change, it can change how those ultrasound waves travel and interact with the tissues, right?
Exactly. For example, if the temperature goes up, the speed of sound in tissue also goes up. And if the density increases, the speed of sound usually goes down. Knowing these relationships helps us understand how ultrasound behaves in different tissues and situations.
I'm really starting to appreciate how closely tied physics is to ultrasound imaging. This one asks about spatial pulse length. What is that, and why is it important?
Spatial pulse length is just the physical length of an ultrasound pulse as it moves through space. Think of it as a little burst of sound energy. The spatial pulse length is how long that burst is from front to back. It depends on how many cycles are in the pulse and the wavelength of the sound wave.
So a shorter spatial pulse length would be like a more compact burst of ultrasound energy. What's the advantage of that?
You've got it. And here's the key. A shorter spatial pulse length gives you better axial resolution. Remember, axial resolution is all about being able to separate objects that are close to each other along the beam's path. A shorter pulse lets us see those objects more clearly.
That's why it's so important to have transducers that can create those short pulses. Now, this one is about beam steering. It wants an example of a technology that uses mechanical beam steering. I thought we were mostly focusing on electronic steering, like with phased arrays.
Phased arrays are definitely the most common these days, but it's used to know a little about mechanical steering too. Mechanical steering means actually moving the transducer elements to sweep the beam across the area you're looking at. A classic example is the annular array transducer.
So with annular arrays, there are actually parts moving inside the transducer to steer the beam.
Exactly. In an annular array, the elements are arranged in these rings, like a bullseye, and to steer the beam, they actually physically rotate or rock those rings. It's kind of like an old radar dish that spins around to scan.
That makes sense. So phased arrays are more like agile and versatile, while annular arrays are more old-school mechanical.
You got it. Each technology has its pluses and minuses, and which transducer you use often depends on what you're trying to image.
Okay, this one asks about the average pulse repetition frequency, or PRF, of an ultrasound machine. What is that, and why is it important?
Pulse repetition frequency is just how many ultrasound pulses the transducer sends out every second. Think of it as the heart rate of the ultrasound machine, how many beats per second.
So a higher PRF means we can see deeper into the body.
Not quite. There's a trade-off here. A higher PRF lets us sample those echoes more often, which is good for certain things like Doppler, but it also means there's less time for those echoes to come back from deeper structures.
So if we crank up the PRF too high, we might miss those echoes from deep down because they haven't had time to get back to the transducer before the next pulse is sent out.
Exactly. It's like trying to have a conversation with someone who keeps interrupting you before you can finish your thought. Picking the right PRF is about finding that sweet spot between sampling rate and imaging depth.
That's a great analogy. I'm starting to see that ultrasound physics is all about finding the right balance between all these different factors. Now, this one mentions PZT, or lead zirconate titanate. Why is that material so important in ultrasound?
PZT is a piezoelectric material. It's a fancy way of saying it has a special ability. It can change mechanical energy into electrical energy, and vice versa. That's the magic behind how ultrasound transducers work. When you apply an electrical signal to a PZT crystal, it vibrates and creates those sound waves we use for imaging. And then, when those sound waves or echoes come back to the transducer, they make the PZT crystal vibrate again, which creates an electrical signal that can be turned into an image.
So PZT is like a two-way street for energy conversion. It's both the speaker and the microphone of the ultrasound world. That's fascinating. Okay, this one is about wave amplitude and intensity. I always get those two mixed up. Can you explain the difference and how they're related?
Imagine a wave in the ocean. The amplitude is the height of the wave, from the top of the crest down to the resting water level. Intensity, on the other hand, is a measure of the energy that wave is carrying. A higher amplitude wave usually has more energy, so it has higher intensity. Think about a little ripple on a lake compared to a huge crashing wave in the ocean. That crashing wave definitely has more energy.
So a higher amplitude wave would have more energy and therefore a higher intensity. Is there a specific relationship between them?
There is. Intensity is proportional to the square of the amplitude. So if you double the amplitude of the wave, you actually quadruple its intensity.
Wow, that's a pretty powerful relationship. It reminds me how a small change in one thing can have a big impact on another in physics. Now, this one mentions Snell's law, which sounds kind of intimidating. What does Snell's law all have?
Snell's law describes how sound waves bend or refract when they go from one material to another, like from one type of tissue to another. Remember that straw in the glass of water? Snell's law explains why the straw looks like it bends where it enters the water.
So it's like a mathematical formula for how sound waves navigate those boundaries between different tissues.
Exactly. Snell's law looks at the angle that the sound wave hits the boundary and the speeds of sound in those two materials to predict how much the wave will bend.
Okay, that makes sense. This one is about bit depth, which is apparently important for grayscale displays. What does that mean and why should I care about it?
Bit depth is just how many bits are used to represent each pixel in the image. In ultrasound, each pixel corresponds to a tiny piece of tissue, and the bit depth determines how many shades of gray you have to represent the echoes from that tissue. A higher bit depth means more shades of gray, which gives you a smoother, more detailed image. It's like having a bigger box of crayons. The more colors you have, the more detailed and realistic your drawing can be.
So it's like having more shades of gray to paint with, which means a more realistic image. This one asks about what happens when an ultrasound beam hits an interface at a perpendicular angle. What's so special about that?
When the ultrasound beam hits straight on, or at a 90-degree angle, there's no refraction. Remember, refraction is the bending of the sound waves as they pass from one material to another.
So it's like a special case where those sound waves don't get redirected.
Exactly. When the beam hits at a right angle, the sound waves either go straight through or they get reflected back along the same path. It depends on the difference in acoustic impedance between the two tissues.
Okay, that clears things up. This one mentions a technique called weak echo rejection. What is that, and why is it useful in ultrasound?
Weak echo rejection is a way to get rid of those really low amplitude echoes in the image. It's like turning down the background noise so you can hear the conversation better.
So it's like cleaning up the image by getting rid of the clutter.
Exactly. Weak echo rejection helps improve the contrast and make those subtle structures that might be hiding behind all those weak echoes easier to see.
That's a great tool to have in your arsenal. This one is about how hypoecho structures look in an ultrasound image. Can you remind me what hypoecho means again?
Hypoechoic structures are just structures that produce weaker echoes compared to the tissues around them. They look darker on the image because those weaker echoes are represented by darker shades of gray.
So it's all relative to the echogenicity of what's around it. What makes a structure hypoechoic?
How echogenic something is depends on its acoustic properties, things like density and how it reflects sound waves. A structure might be hypoechoic because it's less dense or because it's made of stuff that absorbs more sound energy.
I'm starting to see how all these factors come together to create the final look of that ultrasound image. This one's about color Doppler again. It asks if blue in color Doppler always represents venous flow. Is that a trick question?
It's not a trick question, but it does point out a common misconception. Remember, blue in color Doppler just means the flow is going in the opposite direction from the color red, which is usually the color for flow towards the transducer. It doesn't automatically mean it's venous flow.
So it's all about the relative direction of flow, not whether it's in a vein or artery. How do I make sure I don't make that mistake when I'm looking at color Doppler images?
The key is to pay attention to that color bar on the screen and think about the anatomy. The color bar will tell you which color is which, towards or away from the transducer. And if you know the anatomy of the area you're scanning, you can figure out if the vessels you're seeing are arteries or veins.
Okay, that makes sense. It's all about putting the pieces together. This one wants us to actually calculate the velocity of a reflector using the Doppler equation. Can you walk me through how that equation works?
The Doppler equation can look scary at first, but it's basically just a way to relate the Doppler shift, which is how much the frequency changes because of motion, to the velocity of the reflector.
Okay, but how do we actually use it to find the velocity?
The equation uses a few variables: the Doppler shift, which we can measure from the ultrasound signal, the speed of sound in tissue, which we already know, the frequency of the ultrasound wave that the machine sends out, and the angle between the ultrasound beam and the direction of flow, which we can estimate from the image.
So if we know those four things, we can plug them into the equation and get the velocity of the blood or tissue that's moving. That's amazing.
Exactly, and that's how we use Doppler ultrasound to measure things like blood flow in arteries and veins, see how heart valves are working, and even track the movement of fetal heartbeats.
This is so cool. I feel like I'm really starting to understand how we use the physics of sound waves to make these incredible images and get all this clinical information. Now this one takes us back to the basics of wave motion. It asks about the direction of particle movement in a transverse wave. Can you remind me what a transverse wave is and how it's different from a longitudinal wave?
In a transverse wave, the particles in the medium vibrate perpendicular, or at a right angle, to the direction that the wave is traveling. Like, imagine you're holding a rope and you flip your wrist up and down. The wave travels along the rope horizontally, but the particles in the rope are actually moving up and down. In a longitudinal wave, the particles vibrate in the same direction that the wave is traveling. Think of a slinky. When you push and pull on one end, the wave travels along the slinky, and the coils of the slinky are also moving back and forth in that same direction.
So ultrasound waves, which are sound waves, are longitudinal waves.
Exactly. That means the particles in the tissues are vibrating back and forth in the same direction as the ultrasound beam.
Okay, that makes sense. This one asks about intensity and how it's related to power and beam area. I'm a little fuzzy on that. Can you clarify that relationship for me?
Intensity is basically a measure of how concentrated the sound energy is. It's like comparing a spotlight to a floodlight. The spotlight has much higher intensity because that light energy is focused into a smaller area.
So if you have the same power output, a narrower beam would have higher intensity.
You got it. And that's why focusing the ultrasound beam is so important. It concentrates that sound energy into a smaller spot, which increases the intensity right at the focal point and gives you better resolution in that area.
This is starting to feel like a detective story. Each question unlocks another clue about how ultrasound works. Okay, this one asks about the relationship between frequency and wavelength. Can you refresh my memory on how those two are connected?
Frequency and wavelength are inversely proportional. That means when one goes up, the other one goes down. Think of it like a seesaw. When one side goes up, the other side has to go down.
So if the speed of sound in a particular tissue is constant, a higher frequency wave would have a shorter wavelength.
Exactly. And that relationship is important for ultrasound because it explains why those higher frequency waves give you better resolution, but they don't penetrate as deep into tissues. Lower frequency waves, they don't give you quite as much detail, but they can travel further.
It's all about picking the right frequency for the job. This one is about axial resolution testing. It asks which rod group would be used to test axial resolution. Can you explain what axial resolution testing is and how it works?
Axial resolution testing is how we check if the ultrasound system can tell apart two objects that are close together along the direction of the beam. It's like checking how good its depth perception is. We use a special phantom that has groups of rods in it, spaced at specific distances.
So if the system has good axial resolution, you'll be able to see each rod clearly, even when they're close together. But what does that have to do with rod groups?
The rod group you use for axial resolution testing is the one where the rods are lined up parallel to the direction of the beam. That way you're testing exactly how well the system can separate things along that path. If the rods start to blur together, it means the axial resolution isn't so good.
Okay, I see the logic behind that. This one is about B mode in ultrasound. What does B mode stand for and why is it so important?
B mode stands for brightness mode. It's the most common type of ultrasound imaging, and it's what creates those classic black and white images we all think of when we think of ultrasound. In B mode, the brightness of each pixel on the screen represents how strong the echo was from that spot in the body.
So stronger echoes are brighter, weaker echoes are darker, and that's how we get those shades of gray that show all the different tissues and structures.
Exactly. B mode lets us see the anatomy based on how echogenic the different tissues are. Bright areas are things that reflect sound waves really well, like bone or dense tissue. Darker areas are things that absorb more sound energy or don't reflect it as well, like fluid-filled spaces.
This is starting to make so much sense. Okay, quick one. What's the common name for lead zirconate titanate?
PZT.
Right. The wonder material that makes transducers work. Okay, this one asks about pulse duration. Can you remind me what pulse duration is and why it matters?
Pulse duration is just how long that single ultrasound pulse is being sent out by the transducer. Remember, it's like a little burst of energy, and the pulse duration tells us how long that burst lasts.
So a shorter pulse duration means a sharper, more focused burst, which gives us better axial resolution.
You got it. And that's another reason why transducer design and the backing material are so important. They help create those short, efficient pulses, which makes the image quality better overall.
Okay, I'm really starting to connect the dots between all these different concepts. This one is about refraction. What conditions need to be met for refraction to happen in ultrasound?
You need two things for refraction to happen. First, the ultrasound beam has to hit a boundary between two materials where the speed of sound is different. And second, the beam has to hit that boundary at an angle, not straight on.
So it's like the sound wave has to be hitting that boundary at a slant for it to change direction.
Exactly. If the beam hits straight on, there's no refraction. But if it hits at an angle, that wave will bend as it goes from one material to the other.
Okay, that makes sense. This one is about pixel density. How does pixel density relate to ultrasound imaging?
Pixel density is just how many pixels you can fit into a certain area on the ultrasound screen. More pixels per inch means a higher resolution image. It's like comparing an old standard definition TV to a fancy high definition one. The HD TV has more pixels, so the picture is much sharper and more detailed.
So higher pixel density means you can see finer details in the image. Makes sense. Okay, this one is about attenuation again. It asks, how much will a 5 megahertz pulse be attenuated after it goes through 4 centimeters of tissue? Can you remind me how we calculate attenuation?
Attenuation is how much the ultrasound beam weakens as it travels through tissue. It's measured in decibels, or dB. To calculate how much attenuation there is, you need to know the attenuation coefficient of the tissue. That tells you how much the beam weakens for each unit of distance it travels.
So different tissues will have different attenuation coefficients.
Right. Denser tissues, like bone, have higher attenuation coefficients, meaning they weaken the ultrasound beam more quickly. Softer tissues, like fat, have lower coefficients.
Okay, so to find the total attenuation in this example, we would need to know the attenuation coefficient for that specific tissue, and then multiply that by the distance the beam traveled, which is 4 centimeters.
Exactly. And don't forget that higher frequency waves get attenuated more than lower frequency waves.
So that 5 megahertz pulse is going to be attenuated more than a lower frequency pulse traveling the same distance. That's important to remember. Okay, this one is about shadowing. What does shadowing look like in an ultrasound image, and what causes it?
Shadowing looks like a dark area behind something that blocks a lot of the sound energy, like a bone or a calcification. It happens because those dense structures absorb or reflect most of the sound energy, so very little ultrasound gets through to the tissue behind them.
So it's like the structure is literally casting a shadow, blocking our view of what's behind it.
Exactly. And being able to recognize shadowing is important because it can help you identify certain structures and avoid misinterpreting what you're seeing.
This is like a game of ultrasound clue. We're putting all these pieces together to understand how the images are made and what they mean. Okay, this one asks about something called the fast Fourier transform, or FFT. What is that, and how do we use it in ultrasound?
The fast Fourier transform is a math tool we use to analyze signals and break them down into their component frequencies. It's super important for spectral Doppler, where we look at how much the frequencies shift due to moving blood cells to figure out how fast they're moving.
So the FFT helps us make sense of those Doppler signals and get useful information about blood flow. But do we use it for color Doppler too?
Not really. Color Doppler uses a different set of techniques to give us real-time info about the blood flow speed and direction.
Good to know. This one takes us back to the old days of ultrasound. It asks about devices that were used for making hard copies of M-mode images. What is the M-mode, and what kind of devices did they use back then?
M-mode, or motion mode, is a special type of ultrasound imaging that shows you a one-dimensional view of the echoes over time. It's like a graph that shows how the position of a structure changes.
So like a real-time EKG, but for ultrasound.
Great analogy. In the early days, they would often use things like strip chart recorders to make those hard copies.
What are strip chart recorders? I've never even heard of those.
Strip chart recorders use a moving pen to draw the M-mode signal on a long roll of paper. Kind of like a seismograph recording an earthquake, but instead it's recording the movements of stuff inside the body.
That's pretty clever. So as technology got better, they moved on from those strip chart recorders.
Yep. Things like thermal printers and multi-format cameras became more common for capturing and printing those M-mode images.
It's amazing how far ultrasound tech has come. Okay, true or false? In a transverse wave, the particles move parallel to the direction of the wave. What do you think?
That's false. Remember, in a transverse wave, those particles move perpendicular or at a right angle to the direction the wave is traveling. Think of that rope example. The wave moves along the rope, but the particles in the rope are moving up and down.
Got to keep those wave motions straight. This one asks about a specific way to measure intensity that's only used for pulsed ultrasound. What is it, and why is it important?
That would be SEPA, which stands for Spatial Average Pulse Average Intensity. It's the average intensity delivered to the tissues during each pulse.
So it's like the average intensity over both space and time. Why is that important?
SEPA is really important for safety. By knowing how much intensity, on average, is being delivered to the tissues, we can figure out if there's any risk of bioeffects, like tissue heating.
Makes sense. We want to make sure we're using ultrasound in a safe and responsible way. Okay, wow, we've covered a lot. I'm really starting to see how all these little details of ultrasound physics are woven into every part of the imaging process.
That's what makes it so cool. Once you understand those basic principles, everything else starts to click into place.
But we can't get too lost in the physics. In the end, it's all about using ultrasound to help patients, right?
Absolutely. Ultrasound is an incredibly powerful tool, but it's only as good as the person using it. Knowing the physics behind it helps you use ultrasound more effectively, more safely, and with more confidence.
All right, I'm ready for the home stretch. Let's tackle those last few practice questions and wrap up this deep dive. All right, let's knock out these last few questions and see what other gems we can uncover. This one's about those parallel line artifacts again. Can you remind me what causes those? And are there any ways to, minimize them so they don't mess up the image too much?
Those parallel lines, we call them reverberations, they happen when the ultrasound beam gets trapped between two strong reflectors bouncing back and forth.
Like an echo in a canyon, right? Repeating over and over.
Yeah, exactly. Each bounce creates another echo, and those show up as those evenly spaced lines.
So those sound waves are basically playing ping pong. Are there any ways to stop that ping pong match?
Sometimes you can minimize them just by tilting the transducer a little.
Oh, okay.
Kind of like changing your position to break up that echo pattern. Other times you might switch to a different imaging technique that's less likely to have those artifacts.
Good to know. So sometimes a simple change in how you're scanning can make a big difference. This one is about phased array beam steering. Can you remind me how those phased arrays do their thing?
Phased arrays are pretty clever. They have all these little elements that can be fired with tiny time delays. And by controlling those delays really precisely, you can steer and focus the beam electronically, no moving parts needed.
It's like each element is a tiny little dancer, perfectly in sync to create that sweeping beam. Now this one asks about the operator control that adjusts the grayscale range. Is that the same as gain?
That's a good question. It highlights the difference between tweaking the signal coming in versus tweaking what you see on the screen. The control for adjusting the grayscale range is called compression.
Okay.
It's like the contrast setting on your TV. It changes how those echo strengths get mapped to the shades of gray you see. Gain, on the other hand, is boosting the strength of those echoes before they even get to the display.
So compression is fine-tuning the grayscale, and gain is boosting the signal itself. That makes it much clearer. Okay, back to color Doppler. This one says blue always means venous flow. True or false?
Definitely false. Remember, those colors in color Doppler, they don't tell you if it's a vein or an artery directly. They just show you which way the flow is going compared to the transducer. Blue usually means flow away from the transducer. Red means towards it.
Right. It's not about the type of vessel. It's about the direction of flow relative to that ultrasound beam. Got it. This one asks about the matching layer on a transducer. What is that, and why is it important?
The matching layer is a thin layer of material that sits between the piezoelectric element and the face of the transducer. It's kind of like a translator between two languages. It helps make sure those ultrasound waves can travel from the transducer into the body.
So it's like a bridge helping those sound waves cross over from the transducer to the tissues. Why do we need that?
Well, without the matching layer, a lot of the ultrasound energy would just bounce right back into the transducer. That would make the system really inefficient. The matching layer is there to minimize those reflections, so more of that sound energy gets into the body where we want it.
Okay, that makes a lot of sense. Efficient transmission is key for good images. Now this one is about those evenly spaced parallel lines again, those reverberation artifacts. Aside from looking for those lines, are there any other clues that can help me spot them?
One thing to look for is reverberations tend to show up more in areas where you have those strong reflectors, like the walls of a cyst or the surface of a surgical clip.
Right.
So if you see those parallel lines in those kinds of places, there's a good chance it's reverberations.
So location could be a clue. Okay, this one asks about the differences between scanners that use electronic steering and those that use mechanical steering. Can you refresh my memory on the key differences there?
Electronically steered scanners like phased arrays, those are the workhorses these days. They use really sophisticated electronics to control the timing of those pulses to all the individual elements in the transducer. So you get very precise and super fast beam steering all without any moving parts. Mechanical steering is, well, it relies on actually moving the transducer elements around to sweep that beam.
So electronically steered scanners are more agile, more flexible, whereas mechanical steering is kind of more limited?
Yeah, exactly. Electronic steering gives you faster frame rates, more options for how you scan, and you can even create those amazing 3D images.
I'm definitely seeing the advantages of electronic steering. Okay, back to resolution. This one says ultrasound equipment usually has better axial resolution than lateral resolution. Why is that?
That difference comes down to the physics of how that ultrasound pulse works. Axial resolution, remember, that's the ability to tell apart objects along the beam path. It mostly depends on the length of the pulse. Shorter pulses give you sharper detail in the axial direction.
Right, right.
Lateral resolution, that's your side-to-side resolution. That depends more on the width of the beam.
So to improve lateral resolution, you need a narrower beam.
Exactly. And in most ultrasound systems, that pulse length is shorter than the beam width, which is why axial resolution is usually better.
Okay, that makes sense. This one talks about high-frequency ultrasound research, and it mentions a specific material used in those transducers. What is that material and why do they use it?
The material they often use for high-frequency ultrasound research is quartz. Quartz crystals are really good at that piezoelectric effect. They can convert electrical energy to mechanical energy and back again very efficiently.
Interesting.
Plus, they can generate those super short pulses that you need for high-frequency imaging, so researchers can see incredibly fine detail.
So quartz is like the go-to for pushing the boundaries of ultrasound resolution. That's pretty cool. This one's about a device used to measure the intensity profile of an ultrasound beam. What is that device and why is it important?
That device is called a hydrophone. It's essentially a microphone designed to pick up those ultrasound frequencies, kind of like an underwater microphone.
So it's like a microphone for sounds we can't even hear. What do we use it for?
Hydrophones are crucial for safety testing and quality control. With a hydrophone, you can measure the intensity of the beam at different points to make sure it's within safe limits and that the beam is focused the way it should be.
That makes sense. Safety first. Okay, last question. This is a physics brain teaser. It asks, what do you get when you subtract reflected intensity from incident intensity?
The answer is transmitted intensity.
Oh.
So when that ultrasound beam hits a boundary, some of the energy is reflected back and some of it goes through. Transmitted intensity is the part of the beam that keeps on going through that next tissue.
So it's the energy that makes it to the other side.
Exactly. And how much gets transmitted depends on the difference in acoustic impedance between those two tissues.
Wow, this has been an incredible journey. We've explored so much, from the very basics of how sound waves work to all the complexities of transducers and imaging techniques. I feel like I have a whole new understanding of the physics behind ultrasound.
And that understanding is so important. It gives you the knowledge to make smart choices about everything, from picking the right transducer to getting the best images possible. It's the foundation for becoming a truly skilled ultrasound professional.
I couldn't agree more. It's like having that secret key to unlock all the mysteries of those ultrasound images. And on that note, we've reached the end of our deep dive into the world of ultrasound physics. I hope you've enjoyed this exploration as much as we have. Keep those questions coming, stay curious, and never stop learning. Until next time.